So hey guys, it's me Josh, talking about some Abaqus stuff, and welcome to our fourth tutorial, Continuum Elements, in the course Advanced Simulation Techniques in Metal Forming. We have a lot to talk about today, so I want to start with an explanation of this tutorial, so you will see a lot of text. Don't stop listening, please, at least one time. The next time you can directly jump to a specific chapter that you're interested in and don't have to listen to me once again. So I have written a lot of stuff down in these slides so that you can just look it up in case you need it. So for example, on the locking phenomena, on 2D continuum elements, and so on. My guide to a good mesh that I will talk about. So please see this as a help for you to, in the future, that you can quickly get the information you need and don't have to watch videos for hours and hours after a stressful day at the university. Okay, so where are we right now? We talked about the beam elements, we talked about the shell elements, we also mentioned the membrane elements. And in the last Abaqus simulation part, I also talked about rigid elements on the side, which is not very important because rigid is rigid, not so much going on there. So today we'll talk about, I would say, the most important class of elements, the continuum elements or solid elements. And don't be confused. This includes 2D and 3D elements. So we will first talk about very general classifications of continuum elements and later about the 2D continuum elements specifically because they incorporate some special assumptions which make them work. So let's start right away. The most general view on continuum elements basically are listed here. So the number of nodes basically define the interpolation of your nodal DOF, so your nodal degrees of freedom, and over the entire domain of an element, so to say. And that is divided into first and second order interpolation, and basically means that you have one more node along the edges. So this is just a depiction for 2D, but I could equally show you the 3D cases here, which would be then just much more complex. So this is good for a start here. The number of integration points, you cannot give specific numbers here, but you can say reduced is usually or is always of one order less than the full integration. So 1, 4, 4, 9, and so on. So integration points, I think you remember, is used for the stiffness as well as the mass matrix calculation. So this is why people often call this, so to say, the behavior of the element. I haven't decided yet myself if I like the term, but you stumble across it quite often, so I also will use this. But yeah, I think you know from your basic Fem courses what to think when you hear nodal DOF, integration point, stiffness, mass matrix, and so on. The mathematical formulation might be something new to you. We basically have a lot of subcategories here, the mathematical formulations. We've actually talked about this in the previous tutorials when we talked about, for example, Euler-Bernoulli versus Timoshenko, stuff like this. So thick shell versus thin shell theory, and so on. So for continuum elements, we can have the different plane assumptions. that's also plane. So we can have plane stress would be one assumption, plane strain. We'll talk about hybrid elements, hybrid incompatible mode elements. And yeah, these are general, always different mathematical formulations which determine, I would say, the even more general behavior of the elements. Okay, so let's start with first order elements, which can include the reduced as well as the full integration, obviously. They have a constant volumetric strain throughout the element, which is quite often assumption, however, also making this extremely computational efficient. So you assume a certain level of simplification in terms of your volumetric strains, but you also gain a lot. And it's over the years when when the simulations got more and more complex, especially the contacts in these simulations, the first order interpolation elements are almost the go-to guys nowadays, especially since you can, if you want to have a more accurate contact depiction, you usually just refine the mesh in this area. So that is currently state of the art, I would say. Second order elements, you still see this being applied in some special cases, especially for so-called smooth problems. Good question, what it actually means. It can mean a lot and nobody really knows for sure what it means. Sometimes people refer to the contact formulation, the material behavior, the evolution of a deformation process, and so on. So here you can usually have a better depiction of what's going on with far less elements than with the first order element. So, but this should then not include complex contact and severe distortion of the elements, because here the drawbacks, like that it's less robust and might not perform well in contact, come into play. So you should really know when to switch to second order interpolation elements. It's definitely helpful if you have stuff like stress concentrations or geometric features like curve that you want to model with fewer elements, and especially if you have bending, then these really outperform the first order elements. But nowadays, since if we would have this talk a couple of years ago, you would have definitely used this element more often than nowadays, because since computers are so powerful, you often just increase the density of your elements. However, I hope by the end of this tutorial you will also get a feeling for when to not just increase the number of elements by 5, but rather do a smart modeling, because even nowadays, smart modeling and like an educated mesh generation can help you save a lot of time or even give you better, more accurate results. Yeah, so much for the interpolation.